as shown in the figure. This guy rotates by an angular velocity, constant angular velocity omega. Okay? If this guy doesn't rotate, then this is simply a pendulum-like problem. Okay? But this guy rotates, so it makes things more interesting. Write the differential equation of motion for the system in terms of the angle theta. So we have an angle theta here. We need an equation of motion for theta, which means theta double dot equals from the dynamics. Okay? And that's it. And he's asking about the range of omega for stability. You're going to consider this here. Let's get the equations of motion. And we need to see how to start this kind of problems, right? Let's first try to put some axes to well describe our problem. Of course, I'm going to have some maybe N1 inertially fixed axes, N2, and N3 here, okay? Any question about that? Please, if you have any question now, stop me. N1, N2, N3. Any question? Okay. How many rotations do I have? Two. This is the first one, because this guy may not be rotating at all. It's just revolving with the shaft. So this is the first rotation. Maybe some angle here. Now this red plane is the plane of rotation by an angle theta. Okay? So I rotate first to get this vertical red plane, and in that vertical red plane, I'm just rotating vertically. The bar is rotating vertically by an angle theta. So let's name this axis maybe E1. So the N1 rotates to E1. I'll give you some time to write, but you need to follow the description. N1 will rotate to E1. Consequently, these axes are attached to each other. So N2 will rotate the same, get to here, into the board, E2. N3 is the same as E3. Any question about this first rotation? I'm just doing one rotation now. The red rotation to arrive at the vertical red plane. Any question? Yes, please.
So you're rotating the end into the just the rod, right? It's just
Exactly. This is the shaft. Yeah. We call this the shaft, and this is the rod. Okay. And this occurs by a constant angular velocity. It's continuously happening. Okay. Any question about that? Along this vertical plane, let's do it in another side because it's confusing. In this vertical, what is the axis describing this vertical plane? Any plane is described by two axes, right? What are the axes? E1, E3, right? So this is E1, E3. Anybody doesn't agree that the vertical plane is defined by E1, E3? E2 is perpendicular. Where is the rod? The rod is down there. It's like, and actually rotates by an angle theta. Here is your theta, right? So this angle theta, here it is, the same theta here, same theta there, correct? So E1 rotates by theta to some B1, for example, body axis, because I'm done now. It's two rotations and I'm doing the second rotation already. E3 going to B3, body. This theta is about what axis? Yeah, 2 exactly. What is, can you name it to me? What axis? Is it about N2, for example? About E2, positive or negative? We need to think about the sign.
Negative.
Here is theta, right? Use your right hand, please. Here is theta. I'm pointing in this direction. It's the opposite of E2. So this is negative E2, and since the rotation here is about E2 or negative E2, it doesn't matter. This means that B2 is also equal to E2. So the second rotation is about the negative of E2 or the negative of B2. It's the same. Any question about that? Any question? Any question, please?
Can you explain that one again?
Which one?
I don't know how you projected on, sorry, the second graph where, like, are we projecting like on top?
We have 3 lines here, red, blue, and black. Which one you accept or which one you didn't get? Do you accept that the vertical red plane is the E1, E3?
Yes.
Okay, then you accept that the rod is just hanging down there here?
Yes.
Okay, very good. Now the rod initially was vertically down, straight, angle 0 theta, and it rotates like this, right? So I need to rotate these E1, E3 with the rod to get the body axis.
Oh, okay.
Okay? So now I have body axes B1, B2, B3 attached to the rod. They are just located here in a weird way. Hopefully they should be in the center of mass. You can move them if you like. But this is the problem description. We need to agree to the problem description first. I didn't do anything about dynamics now. I'll see how to approach this from a dynamics point of view in a moment. But we need to understand the problem description. Any issue with that? Yes?
Is it wrong if you rotate the E1 an angle of 90 minus theta downwards?
Say it again, please. Sorry?
If you,
E1?
instead of doing B1 and B3, the rotating theta counterclockwise, you rotate clockwise 90 minus theta. Is it wrong if you do it like
So
Just
E1, you put. Do you want to put
that? To put
B1 here? B1 here?
No, yeah, B1 in the direction of the rod.
Okay, let me see. No, I'll tell you something. Okay. You want to do something like, let me use another.
Rotate 90
You want to
minus
do
theta.
something like
Yeah.
this, right?
Yeah.
And this is B1, correct? That's perfectly fine, but please, not to confuse yourself, call this something else, maybe phi, and get the dynamics of phi, okay? And then theta will be pi over 2 minus phi, okay? That's perfectly fine. But I just wanted to stick to the problem definitions, the givens. Which is, yeah, a bit confusing, and I like that. If you can solve the more confusing problem, then you're in good shape. At any rate, any question? Any issue? Let's see how to solve it from a dynamics point of view. So, this is a rigid body. A rigid body has both. How many degrees of freedom a rigid body has? A rigid body, like any mass, can translate with 3 degrees of freedom. So this is 3 translational degrees of freedom governed by Newton's second law. Mass times acceleration of the center of mass equals force. In addition, it has 3 rotational degrees of freedom because this guy can rotate about itself, right? Your chair can rotate if you just throw it in the air, right? So it has additionally 3 degrees of freedom governed by, right? Euler's equation, which is the angular momentum equation. So unlike a point mass, which the angular momentum version was redundant, this is not. You need to use the 2 sets, 3 and 3, 6 equations of motion governing the 6 degrees of freedom. Okay? So I have plenty of equations. I have 3 and 3. And I need to know how can I approach this problem. He's asking about a single degree from theta. I need to get one equation. Apparently there is one relevant equation among these 6. How can I arrive at it in the fastest way, right? This is the question. Because you can simply go and write down Newton's equation of motion, the 3, and the 3 equations here, 6, and try to play them together to get an equation for theta. This is always doable, okay? It's gonna take a lot of time. We need to do it in a clever way, okay? So let's draw. We are still within the same framework of Newtonian mechanics, so you need to draw a free body diagram. These are my body axes, B1, B3. What are the acting forces and moments of this body, please? So the acting forces and moments, well, this is a pin. A pin prevents all the degrees of freedom but one, which is the rotational thing. So it opposes me, it has a reaction forces in all the degrees of freedom, but one. So it has three forces, maybe R1, R3, and R2 to the ball. Right? Reaction forces. What else? Reaction moments. Because it prevents all the degrees of freedom except this degree of freedom. This degree of freedom is about what axis? About what? Come on.
B2.
B2. So it doesn't have any reaction in the any reaction moment about the B2 direction. Okay? But other than that, it prevents all the other degrees of freedom. So there is actually M1 or tau 1, right? And tau 3. And all these reaction forces and torques, they are unknowns. What are the forces acting on this guy?
Gravity.
Gravity, very good. And this is luckily known as mg, thanks to Newton.